So for today, we will be starting with chapter 3 of our book. And in particular, we'll be talking about vectors in 2 space or 3 space and more generally in n space. And we will also talk about some operations on vectors once we know what these vectors are. Although in the previous part of our course, we already had some previews of vectors, and we actually had row vectors and column vectors. So this chapter will generalize these vectors in n space. So, so what are these vectors, particularly in the n-dimensional space or n space? So a vector in an n-dimensional real space, okay, or n space, take note we are only considering real space, and we will denote this real space, the n-dimensional real space, as Rn or R to the n, but sometimes we just call it Rn. So this is an ordered n tuple. So for example, if you are in the 2 space, you just have an ordered pair, just like a pair if you are given a point. Or in the 3 space, we have the triple, just like when we are representing a point. Okay, but the difference between a point and a vector is somewhat notation wise. Okay, and also somewhat this vector thing has more into it than just a point. Okay, so we will see that later, and we will clarify that later. So for a vector, we use bold lowercase letters, okay? Bold lowercase letters, or sometimes a character with a small arrow above that character, okay? And we use them to name a vector. So for example, this is a vector V. So this is a lowercase bold letter V, okay? And if we specify what this vector is, so we have an n tuple here, okay? So the notation will be angle. So this is an angle, okay? Angle, then V1, V2 until Vn. So notice how the V's were written inside these angle brackets, okay? So V1, V2, Vn, because we are in the n-dimensional real space, we have an n tuple. So we have n numbers here, okay? V1, V2, and Vn, and we call this V1, V2, and Vn the components of this vector V. And we say V1 is the first component, V2 is the second component, etc. And if you have a point, remember, if you have a point here, say you have x1 and x2, okay, this is a point. So x1 is called the coordinate, and x2 is also called the coordinate. So here we call x1 and x2 coordinates. Okay, so another difference between vector and point, the names inside their brackets. So for point, we use parentheses. For vectors, we usually use angle brackets or sometimes the square brackets, but we will see that later. And for this course, for me, most of the time, I will be using these angle brackets, okay, to name a vector, okay? So in 2 space and 3 space, a vector is represented by an arrow. So this is the geometric representation of an arrow. So like this is a vector that faces or that has a direction going north. And here you have something direction going northeast, and then here we have something direction going southeast. Okay, and I have mentioned already the direction. It is one of the intrinsic property of a vector. Okay, so the length of the arrow represents the magnitude of the vector. So notice how these arrows have different length. Okay, So the length of that arrow is the magnitude of the vector, and the arrowhead points to the direction of the vector. So as I have said, this one points to the north, this one points to the northeast, and then this one points to the southeast. So different direction for vectors, it means they are different vectors. Okay. And of course, different magnitude for the vectors means they are different uh, vectors. Okay. So again, a vector has a magnitude and a direction. Okay. So any vector is determined by its magnitude and its direction. So if you can give me some direction and a magnitude and you combine them, then you have a unique vector. Okay, you will get a unique vector. Now, since we are already talking geometrically, okay, so we have the following geometric properties. So the tail of the arrow, which is called the initial point. So this is the tail of the arrow, is the initial point of the vector, and the tip of the arrow, the arrowhead, okay, we call it the terminal point. Okay, so geometrically, we can specify a vector by, or we can get a vector by specifying an initial point and a terminal point. So suppose the initial point is at the origin and the terminal point is somewhere at the point P, then we can get the vector from the origin to the point P. That also gives us a vector in the n space. Okay. So if a vector v has an initial point A and a terminal point B, then the vector can be written this way. So remember, as I have said earlier, a vector, it can be named by using a character with an arrowhead above that character. So in here, we have a character AB, okay? And then there's an arrowhead above AB. But this particular naming here, this tells us the actual initial point and terminal point of the vector. So notice from A to B. So the tail for that arrowhead above the character, the tail is for the initial point, and the arrowhead, okay, the arrowhead here is for the terminal point. Okay, so which means if I'm going to write it this way, okay, so you have say AB, then this vector is different from this vector here. So these two vectors are not the same because for this case, the initial point is the vector B and the terminal point is the vector A. Okay, so notice even if I have written A here first before B, but the direction of the arrow is going to the left, okay, so it means that the tail is the rightmost character there, which is B, and then the head is the leftmost character here, A. So for this guy here, AB with the arrowhead going to the right. Initial point is A, terminal point is B. But for this guy here, AB with the arrowhead going to the left, the initial point is B and the terminal point is A. Okay? Was there a question? Let me check that one. Yes, Melissa?
So you said that like if AB with the arrow going from B to A, it's not equal. But what if it was written BA
Yep.
and the arrow going in the same direction?
Then
Would
they are
it
the
be
same. They will be the same.
okay?
If you have
Okay.
something like this, BA, and then you wrote it this way, then this one is the same as this guy here. If we are
Okay.
talking about the same points A and B, okay?
Okay.
If we are
Okay.
talking about the same points A and B. So
Okay.
By convention, when we write a vector using the initial and terminal points, then let us just use arrowhead going to the right, meaning we specify the the initial point to be on the left and the terminal point to be on the right. Okay, so
Okay.
I seldom use this notation here. Okay, I
Okay.
always use the arrow going to the right if I'm going to write it uh, above a character. Okay,
Okay.
yep,
Okay. Thank you.
you're welcome. Other questions or clarifications? So, if the initial point of the vector is the origin, okay, origin, meaning the 0, 0 for the two-dimensional space or the 0, 0, 0 for the three-dimensional space or just 0 or O. We usually write the origin as O or 0, okay? Then we say that the vector is in standard position, okay? So meaning any vector, we can move it to the standard position by stating that the initial point is the origin, okay? And if we have a standard position, if we have a vector in standard position, then the vector is determined by the coordinates of the terminal point, by the coordinates of the terminal point, okay? So what does this mean? So for example, let me just draw it here. So for example, you have this two-dimensional space here, and this is your origin, okay? This is your origin, okay? And say this is your terminal point P, terminal point P, and then you will consider the vector going to that P, okay? So if P has a coordinate, say x comma y, okay, then this vector, let me write this as OP, okay? This vector here, this can be written as x comma y. So that is what is meant in this statement. The vector is determined by the coordinates of the terminal point. Okay. Again, if the vector is in standard position, meaning the initial point is the origin here. So origin going to the point P, it is a vector which we name as OP with an arrowhead above. Okay, and the components of this OP is the coordinates of the point P. So angle bracket x comma y, okay, and whereas the point P here, it's parenthesis x comma y. So two difference, okay, difference between a point and a vector, okay. Now, vectors are said to be equivalent if they have the same magnitude and direction. So I mentioned earlier that if the vectors they have different magnitudes, then definitely they are not the same or they are not equal. Or if the vectors have different direction, then definitely they are different vectors. Okay, so we define equivalent vectors if they have the same magnitude and direction. Okay, so meaning even if they have different initial and terminal points, okay, even if they have different initial and terminal points, if they have the same magnitude, meaning the same length, okay, and the same direction, okay, then the vectors will be equivalent. So these four vectors here, they can be, I have written them in the same Cartesian plane. They are, say, in two space. Okay, so this is our origin. Okay, so this is the two space. Okay, but this has magnitude the same as this, and as this. So they have the same magnitude and they have the same direction as well. Okay, so meaning they are all equivalent. Okay, they are all equivalent. But what's the purpose of this equivalence between vectors? It means that one can be represented by the other. meaning I can remove all the three here and these three here, say these three above this guy here, okay? This can represent all those three vectors here and all other vectors that have the same magnitude and direction as this guy, okay? So you can choose one of them to represent everyone, okay, in the space. So vectors are said to be equivalent if they have the same magnitude and direction. So given the component forms of two vectors, say v1, v2 until vn, and w1, w2 until wn, okay, we say that they are equal. So this time equal, okay? We say that they are equal if they are equal component-wise. So vector v equals vector w if v1 equals w1, v2 equals w2 until vn equals wn. Okay? Now, we have what we call the zero vector. Just like in the matrix, we have the zero matrix. The zero matrix is a matrix which has all entries equal to zero. The zero vector is defined the same, okay? In component wise, but geometrically, okay, the vector whose initial and terminal points coincide is called the zero vector, okay? So you have an initial point and you have a terminal point and they coincide, okay? Then it must be the zero vector, okay? The length of this vector is zero because the initial and terminal points coincide, okay? It's just so this is say this is that vector, okay? This is both the initial and terminal point. So the length of this vector is zero. You cannot get the length of an arrow because initially there's no arrow, okay? And here there is also no direction because again, if you have this guy, you don't know. Is it going to the north, to the east, to the south, to the west, etc. So this is the only vector that has no direction, okay? And the only vector that has length equal to zero, the zero vector. All other vectors, it must have a direction, it must have a length, it must have a magnitude, I mean, okay? And component was, as I have said, all the entries or all the components are zero. So I will be using the bold zero here, okay? And of course, the numbers are just 0, 0, 0, 0, etc. Okay? Okay? Now, just like in the space of matrices, we consider the operations on matrices, we will also consider operations on vectors. So first, we have the addition of vectors. Let us see. So to add two vectors, we will use two rules or two methods. So given two vectors v and w, their sum v plus w may be obtained using any of the following. So first, the triangle position. Okay, the triangle position or triangle position, the triangle rule, I mean. Okay, so what we have is position v and w so that the terminal point of the first vector coincides with the initial point of the second vector. So we want the v plus w. So v is the first vector, w is the second vector. V here, it's your vector, okay? V here, it's your vector. So this is the terminal point of v. And according to triangle rule, we position, okay, we position the second vector, the initial point of the second vector, to the terminal point of the first vector. So this is the second vector w. This is the tail of your w. So the tail of w coincides with the terminal point or the head of v. Okay? So you have the v here and then the w here. Then the vector v plus w, okay, it is the vector whose initial point is the initial point of the first vector. So this is your v, the first vector. This is the initial point of v. So this will also be the initial point of v plus w. Okay? But the terminal point of v plus w will be the terminal point of w, or the terminal point of the second vector. Okay? So this is your v. You attach to the head of v the tail of w. Okay? And then now, to get v plus w, you get the vector whose initial point is v and terminal point w. Okay? So if I'm going to draw this from the beginning, I have the vector v here. Okay, this is the vector v. And I have the vector w here. Then from this point, okay, up to this point, this is your v plus w. Okay, so terminal point of the first vector, okay, is the initial point of the second vector. Okay, and then the vector v plus w, it's the vector whose initial point is the initial point of the first vector and whose terminal point is the terminal point of the second vector. So this is the triangle rule. You form a triangle. Okay, you form a triangle. Okay, take note, if you might see something like the vector v is somewhere here, and then the vector w is somewhere here. Okay, take note that since we define equivalent vectors, okay, we define equivalent vectors, this w here, the vector w here, can be represented by another equivalent vector, and you just call it w again. Okay, and that representation can be obtained by moving this vector w here. Okay, moving this vector w here, okay, to the point there. Okay, and that you have your initial point of w is the same as the terminal point of b. And take note that I moved the entire uh, vector. Okay, it means I did not change the direction, I did not change the magnitude. Therefore, it is equivalent vector to your initial to your w. Okay, so that's how equivalent vectors can be obtained, by moving them. Okay, so this is the first method, the triangle rule. Another method here is the parallelogram rule. So for the parallelogram rule, so remember in here, the triangle rule, we form a triangle. Okay, for the parallelogram, we form a parallelogram. Okay, so for the parallelogram rule, we position v and w so that they have the same initial point. So this is your v, this is your w. They have the same initial point. Okay, the vectors form two adjacent sides of the parallelogram. Okay, so meaning what we're going to do is to copy v. Okay, copy v, attach it to the tail of that copied v. Okay, the copycat v, attach it to the head of your w. So this guy here, is also v. Okay, this guy here, it's also v. And then the same thing for w. You copy w and attach the tail of that copycat to the head of your v. So this is your w also. Okay, and notice that you form a parallelogram. Okay, then you get the diagonal of that parallelogram. Okay, with the initial point of v and w. Okay, so this is your initial point for b and w. Then for the diagonal, you will also use this as the initial point. Okay, And then since you are getting the diagonal, it is from one corner to the other corner. Okay? So here you have this guy here, from this going to that guy here, there. And that will be your V plus W. Okay? That will be your V plus W. Okay? So this is the parallelogram rule. Okay? Notice that I just use the same vectors here. So whether you use parallelogram rule or you use uh, the triangle rule, you will get the same vectors there. Okay? You will get the same V plus W there. Okay? Question. Now, addition of vectors is commutative, meaning you can use the first vector as the second and the second as the first, or etc. So you can interchange the location of two vectors, meaning also that V plus W is the same as W plus V. So in here, V plus W, okay? V plus W, so your first vector is V, second vector is W. So this is the first vector V, okay? So the head of the first vector V is attached to the tail of the second vector W. So this is V plus W. On the other hand, W plus V, this is W. So the first vector is W, okay? And you attach to the head of W the tail of the second vector, which is now V. So this is now V, this now is W plus V. But as you can see, if you see it in the parallelogram rule, they're just the same. Okay? They're just the same. You will still get the same parallelogram and you will get the same diagonal. So V plus W is equal to W plus V. So if you are looking at here, that is your V, you attach W, then you will get V plus W. Or on the other hand, you have W, you attach V, you will still get W plus V. Okay? And they are just the same vectors. Okay? So commutative. Commutative. Addition of vectors is also associative, meaning you can do grouping and you will not destroy the sum. So meaning you have U plus V, you add U plus V first and then add W. It's the same as U, you add it to V plus W. So on the right side, you add V plus W first before you add U. On the left side, you add U plus V first before W. So let us illustrate it here. Um, this is, so on the left hand side, you have U plus V plus W. So we add U and V first. So look, I used here parallelogram rule. Okay, so I put U, V, and W such that I position them such that their initial points are the same. So they are all here. So this is your U, this is the V. Okay, and then look at this. I have a copy of V, attach the tail of a copy of V to the head of U. Okay, to the head of U, and then I will get U plus V. Okay, so this blue vector here, it's your U plus V. And to add W, I have this W, I get a copy of W, attach it to or attach the tail of W to the head of U plus V. Okay, so I will now have the U plus V plus W. Okay, and this red vector is that guy, U plus V plus W. Okay, so this is the left hand side. The right hand side, okay, I now have V plus W first. Okay, V plus W first. So this is your V, this is the W. So I have V plus W. Okay, so this blue vector here, it's your V plus W. Now I get a copy of this V plus W. okay? Because I will add it to the vector u. So the tail of v plus w will be attached to the head of u, okay? So this v plus w is this guy here also. And this now u plus v plus w, and you will get this red vector u plus v plus w. So if you notice, they are just the same vectors. Look at that. Okay? Oops, sorry. So they are the same vector. So you can do grouping. Okay? You can do grouping in the addition of vectors. Keep in mind that the operator must all be addition. If you have subtraction, then it's different. You cannot do associativity with subtraction in there. Okay? So you have u plus v plus w is the same as u plus v plus w. So it is associative. Okay? Of course, this drawing here, okay, it's not a proof. Okay? If I ask you to prove some properties, you cannot use geometric proof. It is not actually a proof. The geometric proof, it's just an illustration to see what is happening in the situation, but it is not a proof. Okay, you still have to write out the statements. Okay, you still have to write out the statements. Okay, so two properties for addition: associativity and commutativity. In the set of matrices, you have associativity, but you don't have commutativity. Okay, the set of matrices, you don't have commutativity, you have associativity, but for vectors, you have both of them. Okay, now we define the negative of a vector. Okay, so given a vector v, the negative of a vector v, which we denote by minus v, the same. Okay, this is the vector with the same magnitude as v. Okay, but the direction is opposite of v. Okay, so 180 degrees rotation. Okay, so if this is going to northeast, the negative will be going to southwest. Okay, so here you have your v, and negative v is the same magnitude but opposite in direction. Okay, and since we have defined what a negative of a vector is, we can define subtraction. Okay, we can define subtraction. So subtraction of vectors, okay, so given vectors v and w, we define the difference v minus w, okay, as the sum of v and negative w. So v minus w, this is defined as v plus negative of w. Okay, so originally you have these vectors v and w. Okay, and then you can get, because of this guy here, we can define the negative of vector, we can define the negative of w. So the same magnitude but opposite in direction. So this is your negative w. And then you are adding v plus negative w, meaning you get a copy of negative w, attach the tail of that copy to the head of v. Okay, so this is still your negative w. Okay, and the sum will be the initial, it will be the vector whose initial point is the initial point of v, and whose terminal point is the terminal point of negative w. So this is your v minus w. Okay, so we started from v plus v and w. We get the negative of w, that is the opposite direction. Okay, then we get a copy of that, attach it to the v, okay, meaning the tail of V, the head of V is attached to the tail of negative W, then you will get your V minus W. Okay? So this is the triangle method. If we look at the parallelogram method, so as I have said, as I have mentioned earlier, the other diagonal, it's actually your V minus W. Yes? Okay? So the two diagonals of the parallelogram, okay? So you have the V plus W, okay? The same initial point as the two vectors. The terminal point is the opposite corner of the parallelogram. That's your V plus W. On the other hand, the V minus W, take note of this, okay? So this is your W and this is your V, okay? This is your V. And how come that the tail of V minus W is the head of the second W? Well, geometrically, let us try to do this. So you have this W in here. Negative of W is somewhat like this. Yeah, somewhat like this. So assuming it's on this opposite direction and the same magnitude. Okay, so this is your negative W. So what is now your V minus W? So you are going to attach this negative W to this part, right? This becomes your negative W. Okay? And therefore, V plus negative W will be this guy here. Yeah? And this guy here, you can move it there. You can move it there. And notice, the tail will be this guy. And the head will become this guy. Yeah? So notice how V minus W is oriented if you put them on a single parallelogram. Okay? Question. So let me just complete this. This is your V, oops, this is your V minus W. Okay? Question. Now, we also define scalar multiple of a vector the same way as we have defined the scalar multiple of a matrix. Okay? So let V be a non-zero vector and K be a scalar. The vector KV, okay, this is the vector whose magnitude is equal to the absolute value of K times the magnitude of V. Okay, so V has a magnitude, the scalar K, you get the absolute value of that, multiply it to the magnitude of V, that becomes the magnitude of KV. Now, the direction will be the same as the direction of V if K is positive, okay? And opposite of V if K is negative. So for example, this is your vector V. So 3 halves V, positive, K is positive, okay? So the same direction as V. But the magnitude will be the magnitude of V times 3 halves, okay? Then here we have negative 2V. K is negative, so negative 2. So the direction will be opposite of V, okay? Opposite the direction of V. And the magnitude will be magnitude of V times absolute value of 2. So twice the magnitude of V, okay? And 1 half V, so positive K, that's positive 1 half. So direction is the same as the direction of V, but this time the magnitude is half the magnitude of V. Okay, so those scalar can shrink or extend your vector. Okay, the direction depends on the sign of your scalar. Okay? Question. So what operations do we have as of now? We have the addition of vectors. We have the subtraction of vectors because we have defined the negative of a vector. And now we have the scalar multiple of a vector. Okay? Scalar multiple of a vector. A vector in two space or three space can be drawn in two-dimensional plane or three-dimensional space. Okay? So for example, in component form, okay, this is your two-dimensional space. Still you have your y-axis and your x-axis. The vector, okay, vector v with components v1 and v2. So we have here. So we can assume that the initial point of v is the origin, meaning v is in standard position. Okay, so you have this vector v. That also means that tip the tip here, okay, that the tip here, if it is the point P, then it is the point with coordinates v1 and v2. Okay, the vector v here, it is the vector with components v1 and v2. Similarly, if you have in tree space, so this is a vector v in the tree space, okay, and we have the x-axis going front and back, okay, so front to back. Y-axis is from left to right. Z-axis is going from down to up. Okay, so this is the orientation of our three-dimensional space. Okay, x-axis is front to back, y-axis left to right, z-axis is down to up. Okay, so in this course, this is the orientation that we will use. Okay, so if this is the vector v, okay, which has component, it was v1, v2, and v3. So v1, v2, v3. This means that the tip of this point here, okay, the tip of this vector here is a point P with coordinates v1, v2, and v3. Okay? Okay? So, yeah.
So how do we like understand which point is for which axis in the three space?
Well, the first is always the x-axis, the second component is always the y-axis, and the third component is always the z-axis.
Okay.
That's it. So let me just let me show you this vector. Uh, just a moment, please. Okay, so here, let me show you this guy here. So this is, okay, are you seeing the graph? So in here you have, so I have written here the vector 1, 4, 3, okay, 1, 4, 3. So the red axis here, it's your x-axis. So positive is going front, negative is going back. The green here, it's your y-axis. So positive is going to the right, negative is going to the left. The blue axis here is your z-axis, positives going upwards, negatives going downwards. Okay, so this is the vector 1, 4, 3 in standard position. So how do we know this? So first, if I move this like this guy here, let me just show you. So notice, okay? So I am looking directly upwards. So I am on top of your z-axis, okay? So notice, this red here, it's your x-axis. The first component is 1, this is your 1. The second component is 4, and this is your 4. The green is your y-axis. So you have 1 in x, you have 4 in y, and that's your vector there. If you are looking on top of your z-axis, okay? Now, suppose I am looking directly in front, okay? So notice, so I'm looking in front, I am considering the green axis and the blue axis. The green axis is y, blue axis is z. So 4, 3. So green, it's 4, z, or the blue, it's 3. So notice that 4 here and then the 3 here. Okay? So that's your z-axis against y-axis. And finally, we suppose we are looking directly from the right. Okay, so this time we are looking on the plane against the x-axis and the z-axis. So again, x-axis is 1, this is 1 here, and z-axis is 3. Okay, and this is 3 here. Okay, so meaning if you have a vector, in the 3 space, you can start projecting. First, what happens in your x and y axis? Cover the z axis. Okay? Or next, what happens in your x and z axis? Cover the y axis. And lastly, what happens in your y and z axis? Cover the x axis. Okay? And then, so you will use your imagination in here, in drawing this three-dimensional object. And then if you combine them, you will obtain this vector here. Okay? So of course, if we go back to this guy here, we don't, it seems it's in the two-dimensional space because this is a flat surface. Okay? This is a flat surface. Okay? But if we look at the drawing, okay, we look at this computer algebra system, still looks on the flat surface, but if you keep on moving them, you will see that it's actually on the three-dimensional space. Okay, so this application, it's GeoGebra. Okay, it's a GeoGebra. You can download it for free. I think it's available both in iOS, in uh, Android, in Windows. So you can download it in your desktop, Windows or Mac, etc. So it is free and you can play with that, okay, to at least visualize your objects in the two-dimensional space or three-dimensional space. Okay? But what if they are not available? What if this computer algebra system is not available? So how do we actually get this vector v? Right? So what we do, so for example, let me just sketch a vector here. So for example, we want to sketch in the three-dimensional space that vector 1, 4, 3. Okay, 1, 4, 3. So what we do, so again, we write the Cartesian plane. We write the Cartesian space, I mean. So I have the Cartesian space here. So this is your z, this is your y, and this is your x. Okay. So this is the z, this is the y, okay, and this is your x. First and foremost, if you are in the three-dimensional space, write the axis correctly. Okay, so going up for the Z, going to the right for the Y, going front for the x-axis. Now, how do we write the vector? So it says you have 1 for the x. So the intersection of the 3, it's always 0. It's your origin. That's your O. That's your O there. So what do we have? 1, 4, 3. So for the x-axis, you go 1 unit. Okay? You go 1 unit. And then for the y-axis, you go 4 units. So 1, 2, 3, 4. Okay? So what you usually do, okay, is to draw lines parallel to the axis. So what I mean, this is your 1 unit here for your x, and you want to work on x against y first. So y is horizontal. That 1 unit for x, you draw horizontal. You draw also horizontal, parallel to the axis. Okay? So that is your horizontal parallel to the y-axis. And similarly, if you have your y, okay, you already have your 4 in y, and since you are working against x-axis, you also draw parallel to the x-axis through that point y equals 4. So parallel to the x-axis is something like this, right? Okay? The intersection of those two parallel lines, so it's this guy here. Take note, it's more to the left. Okay? More to the left of that y equals 4 in your y-axis. Okay? Because the direction of your x is also more to the left. Okay? This direction is more to the left. So this point here, the intersection will be more to the left compared to that y equals 4. So the intersection, this is your point 1, comma 4. Okay? Now, how do we incorporate the z? So z equals 3. So this is your 3 units. 1, 2, 3. This is your 3 for the z. But this time, what you're going to do, the same as before, you write a line parallel to the z-axis, but this time starting from your first intersection, 1, comma 4. Okay? So let me use again blue. So this is your parallel line to that. Sorry, let me remove that. It's not clear. So take note that your parallel line must intersect that first intersection. Okay? So notice this line here intersects the point 1, comma 4. It does not intersect your y equals 4 in this part here. Okay? Because again, it's already moved towards the front. Okay? It has moved it has moved towards to the left because the direction of z is to the left. Okay? Now, you have this vertical line. You draw those three units. But take note, the 1 here is more below that this guy here than this 0 here. Okay? This is your origin here, this point here, and 1 is more below. Okay? So you start with something below. In fact, you will be starting at 1, comma 4. So if this is your 0 unit, okay, if this is your 0 unit, this guy here is your 0 unit, your 1 unit may be somewhere here, your 2 unit may be somewhere here, your third unit is somewhere here. And notice, if this is your third unit, it must be somewhat below also of that 3 in the z-axis. So this is your 3 in the z-axis and it is somewhat below. It is somewhat below here. just like the 1 in here, somewhat below the 0 here. Okay? So this point here, okay, this point here is now your point 1, comma 4, comma 3. Okay? That's your 1, comma 4, comma 3. And finally, your vector is the vector whose initial point is the origin and whose terminal point is that guy. That is your vector 1, 4, 3. Okay? So again, it looks like two-dimensional. It looks like two-dimensional in here, but okay, but it's actually in three-dimensional space. Of course, this drawing I cannot move it. I cannot move it the way I want and the way I do in the computer algebra system, GeoGebra. Okay, so I cannot see the three-dimensional thingy there, but yeah, once you have this way of drawing that vector, you can think of that as a three-dimensional object. So again, if we go back to this cast here, okay, so somewhat our Z is like this. Our drawing was like this. So I think it's totally horizontal for the y-axis. So let me just write it totally. Let us. So it's somewhat like this. Okay. Okay. Although this y-axis here, it's not totally horizontal in this case. Okay, in this case. But yeah, that's the idea. Okay. In our drawing, I wrote y-axis as totally horizontal. Here, this is not totally horizontal. It's actually has an angle below or negative degrees. Okay. But your Z is totally upwards. So anyway, it's fine. Okay. So what observation did we have earlier? First, the tip will be somewhat to the left of 4. Okay. Tip is somewhat, this was your 4 here, but the tip here it's somewhat to the left of 4. And also, the tip is somewhat below 3. Okay. In the two-dimensional thing. So going back to the cast, so this is your 4, this is your tip somewhat to the left, this is your 3, and this is your tip or somewhat below 3. Okay? So question. So you might be asked to draw a vector or a point in the three-dimensional space. And that's how you can do it. You can also start from the z-axis first and then y-axis and then x-axis or etc. Okay, those three actions there are commutative. You can start with any axis first and then the next two axes. Okay, and in the two space it's easier because this is just flat. Okay, this is just flat and there is no somewhat below or somewhat to the left or to the right, etc. This is exactly at V1. This is exactly at V2. Okay. So these vectors, they are in the standard positions. Now, suppose we are given 2 points, P and Q. So we can define the vector with initial point P and terminal point Q as follows. So in 2 space, you have the P with coordinates P1, P2, and Q with coordinates Q1, Q2. And we define the vector V with components Q1 minus P1, Q2 minus P2. Okay? Meaning the initial point is P, the terminal point is Q. So the vector PQ in here, the vector PQ, it's Q1 minus P1, comma Q2 minus P2. Okay? And this vector, will be equivalent to this vector v, red vector here. Okay? So these two vectors are equivalent. And therefore, since this vector is now in standard position, okay, standard position, the tip of this vector here will have coordinates equal to this guy here. So coordinates will be q1 minus p1, comma, q2 minus p2. Okay? If you put it in standard position, the components of the vector become the coordinates of the tip. Okay? If it is not in the standard position, then that is not the case. So P1, P2, initial point, Q, terminal point, Q1, Q2, then the vector PQ. So from P to Q, Q1 minus P1, comma, Q2 minus P2. Okay? In the tree space, so you have initial point P, P1, P2, P3, initial terminal point Q, Q1, Q2, Q3. You define the vector PQ. The components are Q1 minus P1, Q2 minus P2, Q3 minus P3. Okay? So this is not in standard position. The red vector here is now in standard position. And just like before, the tip of this vector here, okay, the tip here is the point with coordinates Q1 minus P2, P1, Q2 minus P2, Q3 minus P3. Okay? Oops, sorry. This is parenthesis. So again, in standard position, the components of your vector become the coordinates of your tip. Okay? If the vector is not in standard position, then you have to find what the tip is or what the initial point is. Okay? Question. Okay? Now, again, we can draw these vectors in 2 space, in 3, and in 3 space because we can imagine them. But on higher dimensional space, 4 space, 5 space, etc., we cannot draw them. Okay? But again, geometrically, they can be represented geometrically in those higher space. It's just that we cannot draw them. Okay? Now, since we have been using the components, we can define these things that we just defined using components. Okay, so for example, so suppose you have the vectors v, v1, v2 until vn, w, w1, w2, wn. They are vectors in Rn, in the n space. And let k be any scalar. Then, the vector v plus w, it's just sum of component-wise. Okay? So the first component will be v1 plus w1. The second component will be v2 plus w2. The last component will be vn plus wn. So you don't have to draw. You don't have to draw these vectors v and w to obtain v plus w. Okay? For the scalar multiplication, you multiply the scalar to every component of your vector. So kv, it's the vector with kv1, kv2, kvn components. Okay? Negative v, it's like negative 1 times v. But negative v, it's the negative of the vector. So you put the negative on every component of your vector v. And therefore, you have your v minus w. So this is the same as V plus negative W. So all you need to do is to subtract the component wise. Okay? So V1 minus W1, V2 minus W2, Vn minus Wn. So it's easier to work on these operations if you have the components of your vectors. Okay? Now, some properties of, of vectors or the space of vectors. Suppose we have three vectors, u, v, w, okay? And we don't care about the components anyway. We'll not be looking at those components yet. And let k and l be scalars. So these properties, you have seen this in matrices, most of them, okay? So they translate to vectors. Because anyway, vectors, it's just n by 1 matrix or 1 by n matrix. Okay? But for vectors, commutativity is valid. Okay? So A here, it's your commutativity. V plus W equals W plus V. Associativity is also valid. U plus V plus W equals U plus V plus W. Now, if we add any vector to the zero vector, we'll get the original vector. So u plus 0, it's the same as 0 plus u, it's equal to u. If we add u and the negative of u, okay, you will get the zero vector. Okay, so u plus negative u, it's equal to the zero vector. Take note, this is a vector. Okay, of course, distributive property of scalar multiplier to the sum of vectors, it's true. So ku plus v, it's equal to ku plus kv. And also, if you distribute a vector over the sum of scalars, so k plus l first, multiply to the vector u, it's the same as ku first, then add it to lu. Okay? So distributive property, so E, distributive property of scalar over the sum of vectors. F, distributive property of a vector over the sum of scalars. Here, it looks like associativity of multiplication, but yeah, you can look at it that way. But in here, on the left-hand side, you multiply L first to the vector U, then you'll get a vector. You can multiply another scalar K. Or in here, on the right-hand side, you multiply the two scalars first, K and L, before multiplying it to the vector U. So they are the same. The scalar 1, if you multiply it to any vector u, you'll still get the vector u. Okay? Scalar negative 1, if you multiply it to u, you will get the negative of u. Okay? Scalar negative 1 multiplied to the vector u, it's equal to the negative of the vector u. The scalar 0, you multiply it to the vector u, you will get the 0 vector. Take note, 0 here, it's the scalar 0. It's the real number 0. Okay? You multiply it to the vector u, you will get the 0 vector. Any scalar k, multiply it to the 0 vector, you will get the 0 vector. Okay? Any scalar k, it's any real number k, multiply it to the 0 vector, you will get the 0 vector. Okay? So these properties, we know this by heart with matrices. Okay? This is the same as that, except for letter A. Letter A is true for vectors, not for matrices. All the rest, they are true for matrices also. We also define linear combination. Okay? So let W be a vector in Rn. We say that W is a linear combination of vectors V1, V2 until Vr in Rn. Take note, the V's here, they are bold letters, okay, lowercase letters, and therefore they are vectors in Rn. Okay, so V1, V2 until Vr, vectors in Rn, if W can be written as this way. So W equals K1 V1 plus K2 V2 until plus KR VR. Okay, and K1, K2 until KR, these are scalars. Okay, so again, similar to matrices. Okay, these scalars, we call them coefficients of the linear combination. Okay, coefficients of the linear combination. If R equals 1, meaning we only have K1, V1. Okay, everything else are 0 here. So W is just K1, V1. Okay, and if we have this case, W equals a scalar multiple of another vector, then we have that definition. We say W is a scalar multiple of V1. Okay, so just like in the previous example, you have your V. We got what? 3 halves V. What was the other example there? You have negative 2V, and then there's a third example, 1 half V. So these 3 halves V, negative 2V, 1 half V, and also V, they are scalar multiple of each other. Okay? If R is 2 or above, okay, if R is greater than 1, then we cannot say W is a scalar multiple. So this definition only happens if you have R equals 1, if you can write the vector this way. Okay? And using this, we define what we call parallel vectors. So we say if W is a scalar multiple of B1, then W and B1 are parallel. Okay? Parallel. Okay? So we write this. We write this as W parallel with V1. Okay? So W is parallel to V1. So that will be the definition. W is scalar multiple of V1, then W and V1 are parallel. And conversely, if W and V1 are parallel, then W must be a scalar multiple of V1. Okay? Question so far? So other notations that we might see, so this is the one that I'll be using most of the time, angle brackets. Okay? In books, you might see this. So instead of angle brackets, they use parentheses. Okay? But I seldom use that because I reserve it for the coordinates of the point. So if I use parentheses, it must be a point on the space. If I use angle brackets, it is a vector on the space. Okay? And again, that is the notation that I will use in this course. In the books, you might see this guy here as a vector. Okay? Yes, Melissa?
So if we're going to be doing exercises from the textbook, how will they write the coordinates if they're writing the vectors in
They will
parentheses?
specify. They will specify if it is a vector or a point.
Okay.
And
Thank you.
sometimes if they don't specify, they use bold letters. Okay? Or they use an arrowhead to say that it's a vector. Okay? Or if it is a point, they just use P or a single letter without arrowhead. So you will eventually realize that they are talking about point or they are talking about vector. Okay. And we have this. We call this the row vector. We had this in the 1 by n matrix. Okay. Or we also have the n by 1 matrix. So it's a column vector. Okay. So most of the time, I'll be using this guy here, the angle brackets, or these two guys here in matrices form. Okay, in matrix forms. Okay, but yeah, you would know that it's always a vector. But for this guy, again, I will rarely use this because I'll be using parentheses as notation for a point. Okay, so let us work on some examples in here. So for the vector, we want to sketch the vector PQ in 2 space or in 3 space. Then find its component. So for example, number one in here. So you have the uh, Cartesian plane. So this is your x-axis. This is that's your y-axis, and this is your x-axis in here. Okay. And we have the point 1, comma 2 for point P. So let me have this 1, 2, 3, and then 1, 2, 3. So point P, 1, comma 2, this is your point P here. Point P there. And then point 2, it's 3, comma 1. So x is 3. Sorry, 1, comma 2. That's wrong. So the point must be somewhere up here. 1, comma 2. Okay, this is your point P. 1, comma 2. So 1 in x, 2 in y. Okay, and then point Q, it's 3, comma 1. So 3 in x, 1 in y. So this is 3 in x, 1 in y. So this is your point Q. Okay, so 3, comma 1. Okay, and the vector will be this guy. So PQ, vector PQ, initial point is P, terminal point is Q. So this is the vector PQ. Okay, this is the vector PQ. So the vector PQ in this case, so if you remember, terminal minus initial in the components. So this will be 3 minus 1, comma 1 minus 2. So PQ, it's the vector 2, comma negative 1. Okay? Let us, very good. That I'm going to, let me see. How do I change this to two-dimensional? So I want to show also the result here in the CAS. I just want to go to the two-dimensional. Yep. So this is the two-dimensional guy. Oops, not really. So how do I go back? Just a moment, please. Yep, I can't go back. Let me see how I can do that. But try to sketch number 2. So I'll just try to reopen this guy here and work on the two-dimensional thing, geometry. Yep, I have this. So here I have the vector with initial point 1 comma 2 and terminal point 3 comma 1. Okay, so I'm gonna share. So this is the vector. So 1 comma 2 and then 3 comma 1. Okay, so this is the vector u. Okay, and notice the vector is 2 comma negative 1. So 2 comma negative 1. And if I'm gonna write that, this vector here, the vector u here, it's the same as the vector 2 comma negative 1. Okay, so this vector here now, the vector v, it's the same or equivalent to vector u. They are equivalent, the same direction, the same magnitude, but v is in standard position. Okay, v is in standard position. Okay, let us go back to the slide. For number 2, so you have here, so number 2 again, let me draw the Cartesian plane. You have the y-axis in here, you have the x-axis in here. This time I have 2 comma negative 2 and negative 1 comma 0. So let me adjust the x-axis somewhere here. Okay, this is negative 1 and then 0. So this point here, negative 1 comma 0, this point here, this is our point Q. Okay, that's the point Q here. And then the point, sorry, I'll put Q above. And then I have 2 comma, what am I writing? Sorry, so the point Q, it's somewhere, it's here. Okay, it's negative 1 on the x, 0 on the y. And then the point P, it's 2 comma negative 2. So 1, 2 for the x, negative 2 on the y. So point P, it's somewhere here. So this is your point P. So let me label again. This is negative 1 comma 0. Point P, this is 2 comma negative 2. Okay? And therefore, the vector will be like this. Oops, what did I show? That will be the vector. So from P to Q, take note of that arrowhead. So P to Q, okay? And the vector PQ, PQ. So again, coordinate-wise, or component-wise, terminal minus initial, so negative 1, comma negative, or sorry, negative 1 minus 2, okay, comma 0 minus negative 2. So you will get here negative 3, comma positive 2. Okay, negative 3, comma positive 2. So again, let us go back to the computer algebra system. Let me, yep, go ahead. Go ahead, your question.
So why is it in the components writing you put the coordinates of of Q before P?
Yes, that's how we defined it. It's always terminal minus initial. That's the definition of writing the vector.
Okay.
Okay. Other question. What was this? 2 comma negative 2. So here we have, so are you seeing this screen? Yep. So you have the point P in here, point Q in here, and you have this vector. Okay. And the vector is negative 3, 2. So negative 3, 2. Okay. And again, if we put this in standard position, we will see that this is this guy here. Okay, so they are the same, or they are equivalent. Okay, they are equivalent. But this guy here is in standard position. Okay, vector W and vector A, they are equivalent. They are in standard position. Okay, for the three-dimensional space, let us see. So for the three-dimensional space, we have the X, the Z axis now going up. We have the Y axis here. So let me name them. Z, Y, and the X axis is going this direction. Okay. So we have the point 1, 1, 2. Let us look at that point 1, 1, 2. So 1 in X, 1 in Y, 2 in Z. So this is 1 in X. Okay. Parallel line. Oops, that's not, they are not parallel there. So take note, I put an angle. Y here is no longer horizontal. It's somewhat tilted downwards. So let me put that parallel vector there. Okay, that is 1 in X. And then using this dotted line here as my new y-axis, I'll get the 1 unit. So this is my 1 unit here. Okay. In the original y-axis, it's more towards to the right. This is your 1 unit there. Okay. So this point here, let me just label it. Let me just label this guy here. This is now the point 1, 1, 0. Okay. Now, to incorporate the 2, okay, incorporate the 2 here. So I will draw a parallel axis to the Z axis. Okay. So this is the parallel axis to the Z axis. Passing through that point 1, 0. Okay. And then I will count 2 units. Okay. On that one. So maybe this is 1 unit in here. The 2 unit is somewhere here. So this point here now, okay, this point in here, this is our point P. So this, no, I'll just use blue. This point in here, this is our point P, 1, 1, 2. Okay, so notice I started with the x-axis, 1 unit, draw parallel to the y-axis, and then count 1 unit from there, and then draw the z-axis from that point of intersection. Okay, and then 2 units. So this is the point P1, 1, 2. And then for the point Q, 0 on X, so it's starting from this point here, origin, then negative 1 for the Y. So negative 1 for the Y. So this guy here, it's negative 1 for the Y. So this point, it's 0, negative 1, 0. Okay? 0, negative 1, 0. And then positive 1 on the Z. So again, draw that Z axis parallel, passing through 0, negative 1, 0, and draw 1 unit. Draw 1 unit. So it must be somewhere here. Let me write it here. Okay. And this is your point Q. And the point Q, so 1 for Z, -1 for Y, and then 0 for X. So notice, it looks like Q is above P, okay? But that's the illusion of your three-dimensional space. So vector PQ is this vector, okay? So this is your vector PQ. So again, it's just the illusion of your three-dimensional space. And we will see that later. So PQ, this is what? Again, terminal minus initial. So 1 minus 0, comma, 1 minus -1, comma, oh sorry, -1 minus 1. So this one is wrong. It's 0 minus 1. So 0 minus 1, comma, -1 minus 1. And then 1 minus 2, comma, 1 minus 2. So this vector is equal to -1, -2, -1. Okay? Question?
Sir,
Yeah.
is it so the X and Y and Z axis, can we choose our own, or it has to be Y to be the horizontal, Z is the top and
Yes, that
okay.
should be the case. To standardize our so it's like cheating if I mean it's not really, but it is somewhat cheating if you just use you change the orientation. Cheating in a sense that if you got the wrong point, the wrong location of your point, then I'll just change the axis. So you get what I mean? So let us stick with this orientation. Your X must be going to front to back, okay? Your Y must be going left to right. Your Z must be going from down, going up, okay? Question. So let me put that now in the three-dimensional. Let us see 3D graphics. So here we are. I'm just going to remove it and then share. Let me share that one. So we are now in the three dimension. So again, I will reorient this. So looking at that green here, it's your notice the green is going to that side. So I'll reorient here. It's like this. I hope red was the x-axis. Okay, let me. So red was the x-axis. Yes, red is the x-axis in here. Y is the green axis. The blue is your z-axis. So let me just input this. So vector 1, comma 1, comma 2, comma vector 0, comma -1, comma 1. Okay. At least in this drawing, it is still clear that 2 is above 1. In my drawing earlier, it was something like this. Okay, it was something like this. So it wasn't clear that 1 is above or 2 is above 1. Okay, but in this graphic, in this computer algebra system, okay, so we have this. Okay, looks two-dimensional, but let us try to rotate it. So look at that one. Okay, look at that direction. Okay. So as you go around, you will see that it's in the three-dimensional thing. Okay. So again, red axis is your x-axis, green axis is your y, blue is your z. Okay. So we have the vector -1, -2, -1. Let us put this in standard position. Vector -1, -2, -1. So this is that vector. So this vector here is equivalent to this vector here. So let us see. So that's actually the orientation. Okay. Okay. Now, what observation can be made on this? So if the first component is negative, then it's going to the left to backwards because x component is negative. It's on the back of your uh, board. Okay. If the second component is negative, it's going to the left. Okay. And if your third component is negative, it's going downwards. So if you combine all the three, negative here, so this is going to the back, going backwards, going to the left, going downwards. Okay. So if we go back to the three-dimensional, so it's going to the left, going downwards. Okay, going downwards. You see that clearly. Okay, going downwards. So this is going downwards and going to the left for y. Okay, and then for x, it's going backwards. This is your forward x. This is your backward x. So going backwards. Okay. Similarly, in the two-dimensional space. Okay, for x and y. +2, -1. Okay, so positive first component going forward here or going to the right, and then -1 going downwards. Take note, this is two-dimensional, so vertical line, that's your y-axis, horizontal line, that's your x-axis. Okay, so positive first component, so going to the right, negative second component going downwards. Okay, in here, negative first component going to the left, positive y component going upwards. Okay, so you can get those observation based on these answers. So you would know if you are drawing them correctly. Okay, and again, this geometric thing, it can be done only in 2 space or 3 space. In higher dimensional space, you cannot just draw them. We don't have a plane or a Cartesian space for higher dimensional spaces. Okay. More examples. I think the rest of the slides for this part are just examples. So we'll just finish this example and then we'll have a break. Then I'll proceed to the second part of the lecture for today. So anyway, so find the terminal of the point, the terminal point of the vector that is equivalent to u equals -1, 2, and whose initial point is 0, 1. So how do we solve this? So we are given the initial point A. Let me use red here. We are given the initial point A with coordinates 0, 1. Let us label the terminal point B as x, y. Okay? And it is said, initial point A, terminal point unknown, but the vector AB is equivalent to the vector U. So this means that AB, the vector AB, initial point is A, terminal point is B. Okay, this is equivalent to the vector U. So you have negative 1, comma 2. Okay, but for this notation here, okay, this can be translated to that can be translated to x minus 0, comma y minus 1. So terminal minus initial. Okay, so this is the vector negative 1, comma 2. Okay, and if they are equal, component wise must be equal. So this means that you have x minus 0. This must be equal to negative 1, and y minus 1 must be equal to positive 2, which gives us x equals negative 1, and what is y? Y equals 3. Okay? Therefore, the terminal point B, so terminal point is, so terminal point,
Sure.
yep,
Why is y all of a sudden 3 when you did y minus 1, you put
equals,
equals 2?
and how do you solve that?
You isolate for y?
Yep. So you put your 1 on the other side, it becomes plus, right? So 2 plus 1 equals 3.
Okay.
So this is your terminal point B. Okay? Here we have the same problem but in the tree space. So terminal point is unknown, initial point A. So let me have this. A, it's 1, 1, negative 3. And let us label B as the terminal point. So this is X, Y, Z. And you want your AB, the vector AB, to be equivalent to 1, 2, comma negative 1. Okay? So again, just like before, to name this terminal minus initial, so you will have x minus 1, and then y minus 1, and then z minus negative 3. So terminal minus initial, and this must be equal to the vector 1, 2, negative 1. And equivalent vector or equal vector, it means component wise equal. So you have x minus 1 equals 1, y minus 1 equals 2, and z minus negative 3. So I'll just write z plus 3 must be equal to negative 1. Okay, so what do we get in here? So x equals 2, y equals 3, and z equals negative 4. Okay, so terminal point will be, so terminal point will be the point, so B with coordinates 2, 3, negative 4. Okay, Okay. Next problem here, find the initial point. So this time we are looking for the initial point given the vector u and the terminal point a. Okay. So in here, we have the initial point, or we have the terminal point a, 0, comma 1. So let me just specify that this is now the terminal point, like in the previous example. Terminal point. So we are looking for the initial point b, x, comma y. Again, let me just specify initial, and our vector now will be BA. Okay, so initial point is B, terminal point is A. This must be equal to -1, comma 2. But this time, the representation BA becomes what? 0 minus x, comma 1 minus y. And this is equal to the vector -1, comma 2. So look at the difference. Initial point is B, terminal point is A. So yeah. So terminal minus initial. Or we will have what? So negative x equals -1. Yep. And y, 1 minus y equals 2. Okay. So this gives us x equals 1 and y equals what? -1. So try to look at that. Check the arithmetic. Therefore, initial point is your B with coordinates 1, comma -1. Okay. I will leave this to you. So you have find the initial point. So same solution as the previous slide, but this time in the tree space. So find the initial point of the vector that is equivalent to V with components 1, 2, -1, and whose terminal point is A with coordinates 1, 1, -3. Sorry, there should be a comma here. That's not 1 minus 3. So there should be a comma here. Okay, and I think in the previous also, I forgot the comma. Let me check. Yeah, I forgot the comma here. So let me put that comma. Okay. So again, I'm leaving this example to you. Okay, same solution as before, as the previous slide. Let us have this 5 in the 5 space. So let U, V, and W be these vectors in the 5 space. So 5-dimensional space. So we want to find the components of 2U minus V and 3W plus 3U. So for number 1, so we want 2U. U it's 1. So 1. Sorry, what is happening in here? So 1, 2, -3, 5, 0. So 2U minus V. So minus V, which is 0, 4, -1, 1, 2. Okay. So if we add them, so let us do this step by step. The first, we multiply this scalar to each of the component here. So that becomes 2, 4, negative 6, 10, 0. Okay? And then minus the vector v. So copy 0, 4, negative 1, 1, 2. Next step, you do the subtraction. Again, I'm writing the complete solution in here. So 2 minus 0, comma 4 minus 4, comma negative 6. So negative 6 minus negative 1, comma 10 minus 1, and finally, comma 0 minus 2. Okay? So applying or doing the operation, we will have what? 2, comma 0, comma negative 5, comma 9, and comma negative 2. So this is the vector 2u minus v. Okay? So for number 2, let us just rewrite 3 times w plus 3v or 3u. So this is equal to 3w plus 9u. Okay? And then let us write this as, so let us put the components now. 3 times w, it's 7. It's 7, 1, negative 4, negative 2, 3. And then plus 9u. U is 1, 2, negative 3, 5, 0. Okay? Then multiply the scalar and then add them. So equals, you have 21, 3, negative 12, negative 6, 9, plus 9, 18, negative 27, 45, and then 0. Okay? And then I'll just add them and give the final answer. So I'll skip this kind of step in here. Okay? So I'll just do the addition immediately. So 21 plus 9, that's 30. 3 plus 18, that's 21. Negative 12 minus 27, that's negative 39. Negative 6 plus 45, that's 39. Okay, that's 39. And then 9 plus 0, that's just 9. So this is the final answer to that sum. 3 times the quantity W plus 3U. Next. Which of the following vectors in R5, if any, is parallel to U, which is negative 2, 1, 0, 3, 5? So choices are 4, 2, 0, 6, 10. So let us try to observe. Parallel scalar multiple. Okay, scalar multiple. Now, look at the components of U. So negative 2, positive 1, and then 0, positive, positive. So meaning, if you multiply a scalar, a non-zero scalar to U, okay, if you multiply a non-zero scalar to U, the first two components must be of different signs. If you multiply a negative number, this becomes positive, this becomes negative. Okay? So notice letter A, the adjacent component here, first component and second component, they are of the same sign. So meaning, it cannot be a scalar multiple of U. So we can remove this guy here. Okay, we can remove immediately this guy. So you got that? Scalar multiple, if you multiply a positive scalar, signs will be retained, negative and positive here. If you multiply a negative number, signs will be reversed. This becomes positive, this becomes negative. But this guy here, it's positive, positive. So this cannot happen. So this cannot be a scalar multiple of U. For letter B, so positive first component, negative second component, third component, it's 0. So any scalar multiple, okay, any scalar multiplied to 0, it's always 0. So at least this is still a good candidate. Here you have positive, positive, but they are both negative, negative. And it seems that this guy here is a candidate for a parallel vector to U. Okay? And in fact, you can check, you can verify that this vector U, or that this vector here for negative 2, 0, negative 6, negative 10, this is actually equal to negative 2 times U. Okay? So try to verify that negative 2 times U, it's equal to this guy here. So indeed, this is parallel. This vector is parallel to U. Okay? And letter C, the 0 vector. And notice that this is just 0 scalar times the vector U. Okay? Any vector, you multiply it to the 0 scalar, it gives you the 0 vector. So this is also a parallel vector.